Hello and welcome to another video. This time the MAP 2015 questions F to J. So these ones, I thought the first five actually were tough in their own way, but some of these I quite like. Now, they do like asking about these functions which take the largest integer less than a value. The opposite of that is this kind of function which takes the largest integer, the smallest integer greater than a value. So, let's put in a number like 7.2 in there. I'm just showing you if that would be equal to 8 if you were doing it the other way round. They're called like floor and ceiling functions, and even the functions which just take away, which just leaves a decimal point. There was a good step question, 2000, step 2, 2021, question 3, I think, where they used a different notation for it. So like 7.2 would equal 0.2. It was like curly brackets. But there's some really good questions on this. They pop up in the extension papers all the time. So you definitely want to get kind of used to dealing with these floor and ceiling functions. Okay, so what have we got here? We're basically saying that we're going to take x over 2 and take away the integer part. That's what we're saying, isn't it? Like we're going to take a number, well, take a number divided by 2, but then take away the integer part of that number divided by 2. Now just think of what that would do to the graph. Integrals in the mat are almost never about integration. They're almost always about finding the area under a graph. Do you know what I mean? But the actual raw integrating, no. Okay, we're going from 0 to 5. So when x is 0, y is obviously 0. And then when you're going all the way up to 2, yeah, it's only when you get to 2 that you're going to have an integer part here to take away, if you see what I mean, because the largest integer less than 0.5 is just 0, so you're taking away nothing. In other words, it's going to be a straight line going up to 2, and when x is 2, well, let's say x is 1.999, we're still going to have the 1.999 over 2 because there's no integer to take away. So it's going to go up to like 1, if you like, over here. And then at that point, it's going to drop back down because once you've got 2.1 here, you're doing 2.1. Let's take 2.2 divided by 2. That's 1.1, but then you're taking away the integer part of 1.1, leaving 0.1. In other words, it's now going to repeat the same process again all the way up to 4. Yeah. Once you get to 4 over 2, let's say you're at 3.99 over, well, let's say you're at 4 over 2. You get 4 over 2, which is 2, but then you're taking away the largest integer less than or equal to 2, and that is 2, and so you go back down to 0. And then from 4 to 5, well, you're going to get halfway up there, aren't you? And so when x is 5, look at it, you can see it. 5 divided by 2 is 2.5. Take away the integer part, you've got a half. Yeah? Okay, so that's what the graph's actually going to look like. And then really, I went through the painful process of just working these from the smallest one, waiting till I got an overestimate. So I tried it with with two strips, and and firstly I actually worked out the area here as well. Yeah, I thought, well, what does the integral actually equal? Well, that's 2 times 1 times a half, which is 1. 2 times 1 times a half, which is 1. And here you've got 1 times a half, which is a quarter. And so the integral actually equals a quarter. Yeah, oh, sorry, 2 and a quarter. Yeah, which is 9 over 4, which is 2.25. Yeah, so I worked that out first, and I thought, right, now I know what I need to get an overestimate. And then I thought, well, what's going to happen with the trapezium rule? They love asking questions about the trapezium rule on the mat. They really do. So make sure you're good with the trapezium rule and how it really works and everything else. Okay, the trapezium rule says strip width over 2. Well, if you're dividing it into 2 equal strips, then this is going to occur at 2.5. Yeah, the strip width is going to be 2.5 divided by 2. And then we've got the ends. Now, these are the end y coordinates. Now, the first y coordinate is 0. But the last y coordinate is when x is 5, and that gives you y as a half. 2 times the middle y coordinates, well, as we're only dealing with one at 2.25, 2.5, let me just make that a bit clearer. That's our only value we need to find a y coordinate of. And when you've got x is 2.5, that's 1.25. Take away the integer part, which is 1, you're going to get 0.25. And that's the only middle in your trapezium rule estimate. Yeah, and so you've got 1.25, half plus a half makes 1, so you've got 1.25. So that's clearly an underestimate. Yeah, that's for 2 strips. But for 3 strips, well, when I did 3, I thought, well, firstly, I'm going to be doing 5 divided by 3 to find where this is here. That's 5 thirds divided by 2, that's 5/6. And then I've got first term 0 again, last term a half again. They're not going to change, but the middles are going to change here. Now we're going to have to find the y coordinates when x is 5/3 and 10/3, because we're basically going 0, 5/3, 10/3, 15/3, which is where x is 5. So what is the y coordinate when x is 5/3? Well, we're going to take away the integer part, leaving 2/3. Oh, sorry, I've got to halve it first as well, because this is the value of x. So this is x, this is f of x. So I need to do f of x divided by 2. 5/3 divided by 2 is 5/6. Take away the integer part, you're going to have 5/6 there. 10/3 divided by 2 is 5/3. Take away the integer part, you're going to leave 2/3 here. So we're going to have 5/6 plus 2/3. Now that's 5/6 plus 4/6, which is 9/6, which is 3/2. Times it by 2, you're going to get 3. So I think you're going to get 3.5 here, which is 7/2. So we're going to get 5/6 times by 7/2, and that is 35/12, which is, I'm sure you can see, just under 3. Before, when I did this, I got 5/2. I'm wondering if I've made a mistake. 0 plus a half. Oh, hang on. I did this very quickly in my head. 5/6 plus 4/6 is 9/6. 9/6 is 3/2. Times by 2, I get 3. 3 plus a half, 3.5. Now, I'm liking this, so I must have made a mistake in my notes here. Happens all the time, actually. Oh, I think I just forgot to add on the half. Yeah. Okay, so I did 3 times by 5, 6, 15, 6. It still ends up being an overestimate, so I think I've got the answer by luck here. But this is an overestimate. And so the answer is B. That is the smallest number of strips for which it produces an overestimate. Well, it's the smallest out of those. It definitely produces an overestimate there, it seems. And so that's that one settled. Okay, this one. This is a classic. It really is. Now, I've lost count on a number of times I ask my students to solve this problem. I say, could you solve for me? Could you draw a graph of sine x equals sine y? Because nobody ever seems to know what it looks like, and I'm not surprised. It's one of those ones which will catch people out. Firstly, what you might do when you're thinking, oh, sine x equals sine y, is inverse sine both sides. So it just looks like y equals x. Well, that's part of it, but it's not the only line which satisfies that. And that's because, why does sine x equals sine y look like that? Well, because if you're solving sine x equals sine y, and sorry to do a related question first, but forget the squares, just try and sketch sine x equals sine y. Well, sure, you invert the sign, so you get x equals y, or whenever you do arcsine, you get more than one answer. You get pi minus y, don't you? 180 minus y, because whenever you're doing inverse sine, you get a value out of your calculator, then you do 180 minus, then you do 360 plus, 720 plus, etc, etc, etc. These are your two principal solutions, if you like, and then you just keep adding multiples of 2 pi. So I'm just going to add multiples of 2 pi. And of course, I can take away 2 pi's as well. So x is minus pi minus y. Or if I go up here, let's move this question to the left a bit. But I hope you see the point I'm making here. Sine x equals sine y is not an easy graph to draw. It confuses people a lot. Now, y minus 4 pi. Can you see that one of these, x has a positive gradient and one of them x has a negative gradient, I think. Yeah, because if I was to rearrange this, these are the ones with negative gradient. If I was to make this y equals, I probably should have done it the other way around. Here, y equals going to be minus pi minus x, y equals pi minus x, y equals 3 pi minus x, y equals 5 pi minus x. These are the y-intercepts. The gradients are always minus 1. These are the y-intercepts. The gradients, they're always 1. And that's why you get this. Yeah, look at that. Y equals x, that line there. This is y equals x plus 2 pi. Here's y equals x minus 2 pi, and then going the other way around. This is y equals pi minus x. This is y equals 3 pi minus x. There's y equals, minus pi minus x, so on and so forth. And you get that lovely looking graph. Well, that is exactly why this one is going to be, well, either B or C looking at that. Let's just quickly have a look at it. essentially what I can deduce from that is that cos x equals cos y, or cos x is minus cos y. Yeah. And then I can do what I did above, but I don't really fancy doing that all again. So I'm just going to point out, well, clearly it goes for the origin, because if x is 0 and y is 0, you're going to get 1 equals 1. That doesn't actually allow us to rule out anything, okay? But you can straight away rule out anything which isn't like constant straight lines for the reason above. Like once you invert the cos there, you're going to get x equals y. So that's definitely going to be part of our solution. So, that one and that one, they're looking good. But you're also going to get x equals, now with cos, you need to do 2 pi minus your first answer. And it might be easier actually if I put the y's and x's the other way around. You're going to get y equals x, but then you're going to get y equals 2 pi minus x. And those are your two principal solutions, if you like. Let me write this one next to it over here. But then you're going to get add 2 pi. You could take away a 2 pi. And so on and so forth. Here you're going to get add 2 pi. You could take away a 2 pi. Y equals minus x. Yeah. And so, it's definitely looking like these two. Can you see they're always going to be straight lines? So it looks like these two are the ones which are the contenders. Now, this one seems to have a solution at, well, for example, this one doesn't have when x is pi, y is 0. Yeah, this is a super fast way of doing this. If you just take that point, when x is pi, we get cos of pi, which is minus 1, but minus 1 squared is obviously going to be the same as 1. Now, y is 0, you get cos of 0 is 1, so you get 1 squared over there. And that's true, isn't it? And that's just from that point lying in the solution set, I can see the answer's got to be C. But yeah, it actually comes from, if you're wondering why pi minus x is an answer there, because it will be y equals pi minus x, it comes from this solution set here, not this one here. Because if you've got this, you can, well, it's a bit more awkward to invert the cos here. You've kind of got to put into minus cos of y is cos of minus y, isn't it? Oh, sorry, let me put it like this. Cos x plus cos y. Maybe it's easier to look at it like this. Cos x plus cos y is going to be equal to 0. And then you can just use the fact that cos of minus 1 plus 1 equals 0. It's easy enough to do them. But you can see that one is the only one which has, a value definitely in the solution set when we plug it in there. Okay, cool. Right, let's actually go on to the next one then. H. This one was really very straightforward, to be honest. How do we handle logs? X squared plus 2. We're going to, that to the power of that is going to be equal to all of that. 4 minus 5x squared minus 6x cubed. I then just expanded the brackets. I thought this basically behaved exactly as I would expect it to. There was nothing really. It was so sort of straightforward, I kind of questioned whether I'd done it right. Okay, put it all on the same side. X to the 4 plus 6x cubed plus 5x squared equals 0. Obviously, we can take out an x squared from that, giving us x squared plus 3x, oh, 6x, what am I talking about? Plus, oh, and have I missed something here? Look at that, I've just, from that line to that line, I've copied that down wrong. And so when I add that onto there, it's actually going to give me a 9x squared. Apologies. That's what you get for rushing. Plus 9 equals 0. That's a perfect square as well, isn't it? X squared, x plus 3 squared. So how many distinct solutions are there? 2. X equals 0 or x equals minus 3. Word of warning though with logs, always check your solutions actually exist, because certain things you can't do with logs. You can't log a negative number, for example. So I did quickly check. Log base 2 of 4, yeah, I can see why that's 2. That's when I'm plugging in x is 0. That works perfectly. And I also plugged in minus 3, and I got log base 11 of, when you work that all out, you actually do get 121. And so, yeah, that clearly equals 2 as well. So there's 2 distinct solutions. What was next? This one. I love this one. Once again, I want to show you something on GeoGebra because it really helps you do this. This one is a great question, and it's there for the students who are good at drawing graphs. Yeah. Now, before I start this, can I just quickly show you what the graph of y equals x squared looks like? Yeah, I'm going to do x squared and x to the power of 4. Okay, I'm just going to bring it over to the screen. Hopefully you can see this. Right, this graph, the one on the inside, at the top at least anyway, this graph is y equals x to the power of 4. Notice, though, that when it's between 0 and 1, it's actually lower than y equals x squared. Yeah, it's got a smaller y coordinate. That's because when you square a number, or do to the power of a 4 of a number less than 1, it gets much, much, much smaller the higher the power you raise it to. Yeah, so let's take a half, for example. When we square a half, we get a quarter. Yeah, so that's going to be a quarter. But when we do a half to the power of 4, we get a 16th, which is significantly lower than a quarter. And that's why x to the power of 4 is under x squared between 0 and 1, but much steeper than x squared after 1. Because, you know, obviously a number bigger than 1 to the power of 4 is much bigger than a number bigger than the same number bigger than 1 to the power of 2. So that's a really important consideration to bear in mind when I'm about to do the next question. So I'm going to draw these three graphs on the same axis, yeah, on the same graph, sorry, and I'm just going to try and count the regions, yeah. I'm going to draw y equals x cubed first, which looks something like this. This is definitely one for people who are good at drawing graphs, and I'm going to draw it in GeoGebra so you can see what I mean afterwards. Now I'm going to try and draw y equals x to the power of 4. Now for just exactly the same reasons that I've just been explaining, it's actually going to be lower than x cubed from 0 to 1, but steeper than x cubed from 1 and above. Yeah, so that's y equals x to the 4. Okay, now I'm going to try draw y equals x to the power of 5. Now, for exactly the same reason, it's going to be steeper than x cubed until you get between minus 1 and 0, and then it's going to flatten out here, and then it's going to be the flattest one for a while. They're all going to go through the point 1, 0. Oh my god, that's so bad. And you're going to be left with like a couple of regions in there. I hope that kind of makes sense. Here's one I drew earlier on GeoGebra. Let's actually draw it on GeoGebra. It's so much easier then. You can see what I mean. My artistic skills are not great. It really does help though if it's better. So there's y equals x cubed, and here's y equals x to the 5. Okay, right. Let's zoom in a little bit. Do you see what I mean? This green line down here is y equals x to the power of 5, which is steepest after 1, but flattest, if you like, before 1. And then this is x to the power of 4, and this is x cubed, yeah, which is the least steep after 1, but the most steep before 1. So now we just got to count the regions. Maybe it's better to do it on my diagram on paper is much better than this. I know probably some of you think I have the worst handwriting in the world. It looks like that when I'm on my tablet, but it really isn't that bad. Let me try and draw it again. So you get a general idea. It's tricky doing this on a stylus. Maybe I should draw the flat one first. So this is x to the power of 5. It gets really, really steep. And it gets really, really flat. And then it gets really, really steep again. This is x to the power of 4. It's going to be not as flat over here and then not as steep. And then you get x cubed. And that's going to be not steeper. Sorry, it's going to be flatter. Something like this. Like that. And so how many regions have we got? Well, we got 1, 2, 3, 4, 5, 6. Remember, we're ignoring the axes, so should I get rid of them now? 7, 8, 9. And this has already been covered. And there we go, we've got 9 regions. It's D. That's how that question actually works. It's a good question, actually. I really enjoyed it. I enjoyed this one as well. This one is not so bad because, I mean, look at this. There's so many different ways you can do this. I like these kind of questions where it's like, well, go on then, which one's the biggest? It's kind of like, it's a cute question. My instinct was to go towards what happens to be the answer straight away because I thought, well, 5 over 4. I just looked at the first two and thought 5 over 4 is 1.25. Square root of 7 has got to be like more than like, you know, I just thought it's probably like, you know, more than 2.5. That's what I was thinking, but I didn't really know. And then I thought, oh, hang on, well, why don't I square both of them? They're both clearly numbers bigger than 1. because the square root of 7 is bigger than 2. And if this is less than 1, well, straight away I can rule it out. But they're both clearly numbers bigger than 1. And when you square numbers bigger than 1, they should maintain their, if x is bigger than y and x and y are bigger than 1, yeah, well then x squared is going to be bigger than y squared, isn't it? Yeah, so we can check the squares, like in fact we can say that's if and only if statement, it provided x and y are both bigger than 1. So I squared this one and I squared this one, and then I thought, well, how can I get to 16? I'll times top and bottom by 4. And then I could see that's definitely bigger than that one, so that kind of rules out that one. Yeah, that rules that out. Brilliant. I know that this is winning at the moment. This looks like the biggest. Cool. Okay, I went to this next and I thought, well, what I'll do is I'll treat this as 10 factorial over the square root of, I thought I'd square that, 9, and I'd square that, so I'll times it by itself like that. Yeah, and then I can put it in a single square root, and this was quite fun to do, over 9 times 6 factorial, 6 factorial. I love tidying up factorials. It's one of the things I do for fun. I've got 10 times 9 times 8 times 7. One of the 6 factorials would cancel that, but then I've got a 9 times 6 times 5 times 4 times 3 times 2. Okay, this is a joy to tidy up because there's so much cancelling to do. Get rid of the 9s. What else can we get rid of? 5 times 2 makes a 10. What else can we get rid of? 8 over 4 makes a 2 on the top, but then I've got a 2 and a 6. Oh well, let's make that a 3 and change that out, and then I've got root 7/9, I think we're looking at that, which is of course square root of 7 over 3. And straight away I thought, great, that's just like square root of 7 over 2, but it's smaller because the denominator's larger, so that rules out that one. It's just like a process of elimination, this really. This one, okay, I've toyed around with the idea of using log laws, but then I thought, well, hang on a second. If this was 32, this would be 5, so this is just under 5, yeah? And if this was 81, this would be 4, so this is just bigger than 4. Now, if you've got a fraction where the bottom number is just under 5 and the top number is just over 4, it must be less than 5 over 4. Can you see that? Because we've made the numerator smaller and the denominator bigger. Hence, that one's ruled out. No chance, no chance. And then it was a toss-up for me between A and E. And this I didn't really, see so quickly. It was like, I was toying with the idea of using like numerical values because I know some of the numerical values of these. It was like, maybe I should use numerical values. I don't know. In the end, I went for a kind of squaring approach. I thought, well, okay, if I square that, I get 7 over 4. And if I square this, I actually end up with 7 plus 2 root 6. Because that squared 7, and then the 2 root 6 over 9. And I thought, well, let's have a common denominator. So I times this by 9, and I times this by 4. And I thought, okay, let's compare this. And then I thought, well, what is the square root of 6? Let's find like the most it can be. It definitely can't be 3. It's got to be smaller than 3. Let's pretend it was 3. This would be 28 plus 24. Yeah, if that was 3, 28 plus 24. And 28 plus 24 is going to be 52, which is less than 63. So even if I made this as big as possible, it's still going to be smaller than that one. So that ruled out that. And so the answer is A, I think. Okay, hope you enjoyed those solutions. I quite enjoyed making that one. The last few were quite good fun. Best of luck in the math. Bye-bye.